So I would like to thank you first for allowing me to present a few results and projects on the phenomenon we are working on, which is magnetospheric accretion in young stars, and that Jean-François introduced already during the SLS presentation. So just to draw the global picture, this is the summary of the magnetic properties of young stars. This is a strong Russell diagram where you can see the magnetic field of here solar type and low mass fully convective stars that have strong fields of the order of a few hundred to a few kilogauss, since they are fully convective and have a strong dynamo. And then at the other extreme, you have these massive Freeman sequence stars that are mostly fully radiative, that do not have or have undetectable magnetic fields. So it seems from these results that have been built over the years, especially with Espadon, that the magnetic field properties of Freeman sequence stars depend strongly on their internal structure. And here we will be concerned with this solar type and low mass Freeman sequence star at a few million years old that have strong and mostly asymmetric and predominantly dipolar magnetic fields. And while they have these magnetic fields, they also at the same time, over a few million years, they have these beautiful circumstellar disks. You can see adaptive optics images here of these disks on the large scale. So the typical scale is a few tenths of astronomical units. So the size of our own solar system. And you see all these spiral arms, gaps, warps, whatever you want, you find in this disk. They are really structured, and the typical interpretation is that all these structures are sculpted by nascent planetary systems on a time scale of a few million years. So the full picture we have of a young solar type stars are these large scale disks, in terms of astronomical units. But when you go down to the center of the system, then the disk which is accreting onto the star encounters this strong stellar magnetosphere, and the magnetic field is strong enough to disrupt the disk actually at a few stellar radii above the stellar surface. And that's simply where the magnetic torque equals or balance the viscous torque in the disk that disrupt the disk, so that the material cannot flow directly to the star in the equatorial plane, but it is forced to follow the magnetic field lines. And this develops accretion funnel flows where the material is free falling onto the star. And when it hits the star, there is a zoom here, it creates an accretion shock. So that's the current model, let's say, for magnetospheric accretion on young stars, which is expected both from their mass accretion rate and from their strong magnetic field. And in more detail, so that's a sketch here. So here you have a dusty material that is in the inner disk that will go into this magnetic funnel flow. So here the dust sublimates because the funnel flow becomes very hot, and therefore you have hot plasma where the emission lines of the objects form. And then you have the accretion shock from which the UV and X-ray emission comes from. So in this picture, and everything takes place on a scale of less than 0.1 astronomical units, that is a few stellar radii. And in fact, most of the properties of this object, they have very peculiar properties, and most of their properties arise from this phenomenon, magnetospheric accretion. And that's why we would like to understand exactly how accretion proceeds from the inner disk to the star. That's one of the reasons. Another reason is that this star-disk interaction probably regulates the angular momentum evolution of young stars. I'm not going to detail this plot. This is rotational velocity as a function of time. This is the sun here, and these are Freeman sequence stars. And during the Freeman sequence phase, even though they are contracting and accreting, and therefore should spin up, they don't spin up, these stars. And we think the reason they are prevented to spin up lies in the star disks, the magnetic star disk interaction. So in order to understand this evolution, we have to understand the star disk interaction process. And another reason, the third reason perhaps, is that this is the magnetospheric accretion at scale. So it's a fraction of a tenth of an AU. And at the same scale, these are the low mass planets discovered by Kepler. So if the low mass planets form early in the life of the star, then they probably interact. They are located in the inner region of the disk, and therefore they might modify the accretion process. And in return, it might be that this magnetospheric cavity modifies or perhaps even promote the formation of low mass planets at the disk inner edge. So that's another reason why we would like to explore this very tiny region compared to the full-scale disk around the star. So how do we do that? Well, again, at this scale, we cannot have direct images of this process. So what we exploit is the time domain, because the star rotates with a rotation period of about 1 week. And this is also the co-rotation period at the inner disk edge, which means that this whole inner system rotates within a few days, typically 6 to 8 days. And therefore, if you follow the system, the variability of the system over 1 or 2 or several rotational cycles, then from the variability you observe, you can infer the structure and the physical conditions in the magnetospheric accretion region. So that's how mostly we try to investigate the physics of this process. What do we expect? We expect from pure photometry, from light curves, if you are looking at this system at high inclination, that is nearly grazing the disk, this accretion curtain, which is described in this MHD model here, will come periodically on the line of sight. This is rotating, and every period, the accretion curtain, which contains dust, will obscure the star. And therefore, that will produce eclipses, periodic eclipses of the central stars. This is what is predicted by the model. This is the type of light curve that is sometimes observed in many objects, actually many objects, which is called dippers because of all these dips that are occurring on the light curve. So that's one way to probe what's happening at this star disk interface here, dippers. Another way is or complementary actually, is to look at spectral variability and especially line profile variability. Because as I said earlier, the part, at least, of these emission lines form in the funnel flow, in the accretion funnel flow that contain this hot plasma, which is free falling onto the line of sight. So the line profile should reflect the geometry of the funnel flow, and their variability should reflect the whole magnetospheric structure. And one specific signature of funnel flows is what we call this inverse specific profile. That is this highly redshifted absorption that develops when the funnel flow is along the line of sight. And the reason you have this strongly redshifted absorption is that you are looking at the upper part of the funnel flow, which absorbs the lower part, which is hotter, and therefore that's absorption. And it's highly redshifted because the material is in free fall velocity in the funnel flow, reaching speeds of a few hundred kilometers per second. So this inverse specific profile, this redshifted absorption, are a signature of the funnel flow. And when they come and go as the star rotates, you can reconstruct essentially the geometry of the funnel flow. You know when it's there, you know at which phase it appears and disappears. So that's what we are doing, essentially, monitoring these systems. And I'll show you a couple of examples. This is one of these young stars, which is called LkCa 15. It is a transition disk system, which means that there is a large circumstellar disk, but there is also a large cavity within this disk, whose size is about 50 astronomical units. And it is suspected that a giant planet has carved this cavity, even though the planet has not yet been detected. So we were interested to know how does magnetospheric accretion proceed in such a system. We know the central star is accreting because we have all the accretion diagnostics present. So we monitor this system. This is the K2 light curve of the system, and we found a little bit surprisingly that it's a dipper. Surprisingly, because as I said earlier, the dipper are expected for high inclination system. And the large scale disk, which is seen by ALMA, is not at high inclination. It's intermediate inclination, like 50 degrees inclination. And the fact that it is a dipper, so that comes from the inner disk, much closer to the star, suggest that the inner disk is misaligned relative to the outer disk. And this is one of the first systems for which that was found. And now there are several systems, especially these transitional disk systems, where the inner and outer disks are misaligned. And here we have the monitoring from CFHT Espadon. You see here, for instance, one of the calcium-2 triplet line. You see the strong variability on the right side of the line. And when you do a periodogram analysis, you find a period of 5.8 days, which is the rotational period of the star, which means that this is, as well as this redshifted absorption in the H-beta profile, these are the signature of rotating funnel flows. And with Espadon, of course, we can do the polarimetric analysis, and we derived a strong dipole field, which is misaligned with the rotational axis, which produced the funnel flow. This is the misalignment between the magnetic and rotational axis that makes the magnetospheric accretion non-axis symmetric and thus produce the funnel flow. And this is exactly what the models predict. When you have an inclined dipole, you should have this kind of signatures. So that's fully consistent with what is expected from the models.
Jerome,
another example.
2 minutes. You have 2 minutes.
Thank you. Another example is V2129 Oph, which is another of this young system. And here we did simultaneous or quasi-simultaneous observation with Pirou and Espadon. And these are, for instance, this is the infrared helium-1 line, and this is patient beta with Pirou, and this is H-alpha, H-beta, and the helium-1 optical line. And you see that we have different signatures. First, this line is extremely interesting because we had this redshifted absorption that probes accretion, but we have the blue shifted absorption that probe the ejection process. So we can probe both accretion and ejection at the same time. And you see that this is the period. So we again find the period of the star in these two diagnostics in the infrared, but in the optical diagnostics, we find another period, which is probably related to winds, perhaps inner winds. So what I mean here is that this optical and infrared observations provide different clues to the magnetospheric process, and we need both, and that's why CFHT vision will be the ultimate instrument to do that. So that's one thing. The other thing is that we, for some systems, we follow over the years, and this one we had observed about 10 years earlier, and we had about the same line profiles. You see the line profiles are very similar, but the periodicity is different, which indicates that on the long term, this magnetospheric accretion region is dynamical. Either the magnetic field change or the accretion rate change or something is varying, and we want to explore that as well. Okay, so in the last minute, I will tell you what we want to do in the SPEEDY project, which is investigate the presence of forming planets at this location, very close to the star embedded in the inner disk. And we develop models and observations. So the kind of models are MHD simulations. And this is what is done by Georges Pantolmos, who is the SPEEDY postdoc at IPAG. So this is star disk interaction. So we can predict the structure of this accretion process. And the next step is to include the planet in these simulations. And then we do atomic line radiative transfer that we plug onto the MHD simulations to predict the line profiles that you see here and to get monochromatic images in each velocity channel of the magnetosphere. And I will show you just a couple of movies of that. This is models. So we put a magnetosphere from the MHD computation. We put hot plasma and we compute within the line profiles. On the left, that's H-alpha, and on the right is bracket gamma. What kind of emission, where is the emission coming from actually in the magnetosphere? Okay, and observationally, now we combine spectropolarimetry with Espadon and Pirou with interferometry, space photometry, and a lot of other things, because we need different diagnostics to really understand what's going on. And I wanted to show you that, but I'll be quick. That's another system, another transitional system. The result essentially is that this time we combine CFHT spectropolarimetry with Pirou and gravity with the 4 UTs on the VLTI. And from interferometry, we could put an upper limit to the size of the magnetosphere directly from the interferometric signal, which we find is less than 5 stellar radii. And from spectropolarimetry, by reconstructing the magnetic field, we can estimate the size of the magnetosphere, which we find should be 4.6 stellar radia, which is fully consistent with interferometry. So that's by combining these different techniques that we learn really the details of the magnetospheric accretion process. So to conclude, just to say that we need this multi-technique, multi-wavelength approach, and that CFHC, Espadon, and Spirou, of course, are the only instruments that are so good as providing us with the magnetic topology and strength, obviously. And this is the crucial parameter in the magnetospheric accretion process, obviously, magnetic field. And we are now developing the models that will allow us to quantitatively compare the observations with the model prediction. So we have still a lot to do, and I would like to thank all of these people, and there are many more that have been associated to these studies. Thank you.
Thank you. One very quick question. Jean-François?
Yeah, on V2129 Oph, you were showing this signal at 8 days or so. That is longer than the rotation period. And was it H alpha? So it can't be linked to the star itself, because otherwise it would be the stellar rotation period. So it has to come from the disk. So is it is it possible that it would probe the presence of something there, and possibly a giant planet that would change the accretion rate, or so much as to generate a signature in H alpha at some point?
Yes, well, it's a very strong signature in H alpha. So we think it's still a part of the stellar system in some sense, and it's presumably it's inner wind, which starts from the accretion disk, but from the inner part of the accretion disk at a Keplerian radius that corresponds to these 8-day periods instead of the stellar period, which is 6.5 days. But the hope essentially will be to, by investigating this signature, to eventually find a planetary signature. But it will be weak compared to what we see here, and that's why it's difficult. But as Etienne was saying,